All right. Well, let's go ahead and get rolling for today. So I'm going to start every day off with a riddle because I think it's a decent way to focus everyone. And then I'll usually have some announcements, and then we'll go from there. Okay, so our riddle for today: what is bought by the yard but worn by the foot? No, you don't buy it by the yard. You don't buy socks by the yard. Huh? Anyone? You're not yeah. Carpet, exactly. Carpet is you don't wear carpet on your feet, but you wear it out with your feet. So it's worn. But I know. Don't worry, they will get actually worse. Okay. All right, so today, some announcements. Let me go here. Let me go ahead and back up. So hopefully all of you saw the announcement in Canvas. I said that there's a possibility that I might change some things on the syllabus because I had some idea and I have decided to pursue that idea. I think it's a better way to teach this class. So I have placed on Canvas a changed syllabus. I highlighted in very obvious ways the changes. It's not too big of a change, but I do want to make sure that you're aware of it and that I've informed you of this. This is what I went through on Wednesday, and the changes are obviously highlighted here in red. So what we're going to do is we're going to take 5 different days throughout the semester, and we're going to devote that day to an in-class group activity. You'll be working in groups of 3. Okay, you will have to be present to get credit for that. We'll give you a lot more details on what the assignment is going to be, but I think it's a better way to teach you metabolism on those 5 days in particular. Okay, they will be worth 10 points. My idea is to get those done, to get that assignment done and turned in before the end of the class. That would be the way I'm going to design it. So it's not like it's homework, but it'll be in-class work. That's the idea anyway. We'll see how it works because I've never done this before. They're going to be each worth 10 points. I'm going to only count 40 points though. So I'm going to drop your lowest one. So let's say you miss one, then we will just go ahead and drop that for you. I will make announcements beforehand in terms of when they will be. It's going to be hard for me to know exactly when they're going to land because it's going to be dependent on where I am in the material. All right, so the first one I believe is the first day that we start covering glycolysis, which I believe is February 1st, but I'd have to go look at the syllabus again. But it's the very first day that I have scheduled to start discussing glycolysis. That will be our first group work assignment. Okay. And you'll get obviously a lot more instructions when we get there. Now, that is also going to then impact the exams. I'm going to reduce the exam point total by 10 points on each exam, so they'll only be worth 90 points. You'll notice then, because there's 4 exams that are now not at 100 points, but they're at 90 points, and I'm adding 40 points here, the total point change in the class is not changing at all. It's still 525 points. The nice thing about this, I think, for you all, is that it will make the exams shorter. And one of the things that over the last couple of semesters that my students have always had a difficulty in this class is that the time given to take the exams is usually too short. So I've been trying to reduce that exam material, and this is another way to do that. Okay, so that's the change. Please look at the syllabus if you haven't done so already, and go ahead and read on that. I think that it's pretty straightforward, though, the change. Okay. Now, another thing that I wanted to mention, I said on Wednesday, I said that quizzes 1 through 4 were going to be due on the 24th. Red check minus. That I should have said quizzes 1 through 3 will be due on the 24th. The 4th one will be due on the 31st. So if that caused confusion for you, I hope that clears it up. Okay. The other thing along those lines, those quizzes 1 and 2 in particular, are on those review tutorials that I have posted on Canvas and I'm not doing in class. Okay, so listen to those. Okay, all right. I think that's it. Any questions on those changes or anything to that effect? No? Okay. Let me scroll down here then and pick up where we left off on material on Wednesday. So we left off essentially right here On Wednesday, we essentially just broadly categorized the types of metabolic pathways, anabolic and catabolic, and then I tried to give you at least some sense or some appreciation that there is a massive number of pathways in any one given cell, and that those pathways are going to operate not in isolation but in coordination with one another. So that means there's this massive undertaking in terms of regulation of metabolic pathways with respect to one another. So, you know, some pathways will be upregulated while some pathways are downregulated at the same time. We want to discuss how does that happen, not in a gory amount of detail, but we certainly do want to address some of those details in this class. Not only that, but if you then start to look beyond just what's going on in a single cell, if you look at a multicellular organism, a complex one like you and I, then there's a massive undertaking of regulation of metabolism at an organ or a tissue level, that some tissues are going to have increases or decreases in different types of pathways and different outputs based off of the needs of the body. And that can be done in a variety of ways. Hormonal regulation is very common in that. We are going to be not addressing a lot of hormonal regulation. We'll talk certainly about insulin, certainly about glucagon and epinephrine in this class. We won't extend too much beyond that. There's certainly more than that, but we won't extend too much beyond that. This is not an endocrinology type of a class. Okay? All right, but that's then what we discussed on Wednesday. What we want to do today, we want to essentially talk about certainly these two things, give us some very general idea about how a metabolic pathway has been designed so that regulation can occur. So that's what we're going to do, and that will bring up this concept of flux control coefficient, which your book discusses. Moving from there, and this will finish out our chapter or our lecture 1 material, we'll actually talk about how can regulation occur. Again, using general terms, and these are the 4 things that we will discuss in that regard. All right, so let's go ahead and start with this, but even before we do that, let's discuss this term steady state. This is a very important concept, not only certainly in a metabolism class, but really in any biological class. All biological organisms are at what's called a steady state. You may have heard this described as homeostasis, or you've heard it in conjunction with that word, homeostasis. But a steady state is just simply this. It's a non-equilibrium state of a system through which matter is flowing where components remain at constant concentration. I'm going to try and illustrate this, but let's just make sure that we all have this down. I'll illustrate this. So a non-equilibrium state of a system through which matter is flowing where components remain at constant concentration. Okay. A couple of words to highlight there. That will be talking points. Non-equilibrium state, components remain at constant concentration. Okay. You and I are not at equilibrium, meaning that the biochemical processes in our cells have not reached equilibrium. If that was true, you would not be taking notes right now. You would be 6 feet under. Okay? Equilibrium from that standpoint in a human being or in a biological organism means that that organism is dead. Okay? So keep that in mind. You are maintaining a steady state. Now, by equilibrium, we're using a technical definition of equilibrium that you should have gotten in general chemistry, that the rates of the forward and reverse reactions are equal. That's what we mean by equilibrium. Okay? We don't mean that the product and reactants of the concentration are equal. That's not what we mean. Okay? We mean forward and reverse rates are equal. And that's not true. That's true of some of our reactions, but certainly a metabolic pathway that will not be true of. All right, now I want to go ahead and illustrate a steady state here. And to do that, let's first of all, though, ask a question, because this will bring up, I think this is a really fascinating question. And I should have asked this question first. I'll do that later. Well, remind me. And if I don't do it today, then I'll do it another time. But let's do this. How many pounds of ATP do you think you will use today? And you should know that. I mean, this should be common knowledge. How many pounds of ATP are you going to use today in a 24-hour period? I'm going to let you think about that. I'm going to let you talk to your neighbor about that. Give me a numerical answer. You don't have to put units, because I've already given the units. Just give me a numerical answer. What do you think? How many pounds of ATP are you going to use today? Minute and a half. On your marks, get set, go. Okay, about 10 seconds left, so submit an answer if you haven't done so already, and then we'll check it out. Okay, let's check this out and see what answers I got. Here we go. Okay, 80% of your body weight. 30,000. Very nice. That's the right answer. 30,000. 30 pounds, 420, 25, half a pound, about 100 probably, 100,000. Lots of people put the geek. So what you want to do is you text the number, you text the geek to that, and then after that you text your answer to the same number. Okay. I mean, that's an interesting answer, but the wrong answer. Okay, 300 pounds, 3,000, 0.7, 13. I mean, we got all sorts of... Oh, we got Avogadro's number up there. That in pounds... So many. Good one. So many. So many. Okay, so... All right, so let's go back to my presentation here. Where is it? Okay, so I'll pull up a blank slide. It's a fun question. I certainly don't expect you to know the answer to that question. And obviously it would vary for every individual, and it would vary based off of the activity of your day. However, it is an astounding number. It's about 120 pounds on average for a college student. Right? Now, some of you are like you were just joking when you said about 100, right? So, but no, it's about 120 pounds. Now, when I first encountered that number, I said, that's wrong. That can't be right. So I looked at the calculation. I even did the calculation myself to try and convince myself that that was true, and I was actually convinced that that is right. Now, I think that what you think of when you think of 120 pounds, you think to yourself, okay, that means I have to store 120 pounds of ATP somewhere around here, right? And then I just kind of like a chipmunk go and find it, you know, and use it as we go along. And that's not really the way you should be thinking about that 120 pounds. You don't have 120 pounds of ATP on you right now. But what you do have is a massive capacity to regenerate the ATP that you use. Right? So you will burn it, and then you will regenerate it, and you'll burn it, and you'll regenerate it. So let me do this, and let me go ahead and draw this for you to try and give you some idea of what we mean in terms of a steady state. And so what I'm going to do, I'm going to first of all just draw, and let's just pretend that we have these tanks, and within these tanks is liquid. And that liquid is going to represent ATP. And you say to yourself, is ATP a liquid? Don't say that. Don't even think that. That's not what I'm trying to say. That's just not what I'm trying to give you an idea of. But okay, so we'll just leave it at that. Okay, so that's not what I'm trying to say. All right, but we've got these two tanks, and we're going to put in this upper tank a really high level of the liquid ATP. Okay, and then we're going to put down here in this lower tank, we're going to put a fairly low level of ATP, ADP, and inorganic phosphate. Okay, and you say, what did he just write up there? I wrote this, ADP plus inorganic phosphate. In fact, the reaction that I'm really driving at here, and I'm not going to write it in all its wonderful glory here, but ATP goes to ADP and inorganic phosphate. Okay, ATP, adenosine triphosphate, ADP, the breakdown product we take off of phosphate. Okay. You actually have to have water to do this, and you produce a proton, so this is not a balanced chemical equation, but I think that will suffice here. Now, what I'm trying to illustrate here is this, that we have in these series of tanks a non-equilibrium state, and we can tell that if you think about this red stuff here as a liquid, you know that it's going to drain into this. Gravity is going to take over, it's going to drain into that. In fact, it will drain into this to the point where it will reach some equilibrium state. Okay? Draw this out. So finally, we have now ADP and inorganic phosphate, and we just have this tiny little amount of ATP here. Okay? Maybe just a surface level of ATP. And I've drawn these tanks purposely with tops on them. They're closed. Okay? Now, what I have on the left here, this would be a non-equilibrium state of the ATP reaction. You have a lot of it at non-equilibrium, and there's not very much breakdown product. Right? The delta G of ATP demands that at equilibrium there will be hardly any ATP left. Because if you let ATP be hydrolyzed until finally it reaches equilibrium, there will be no ATP left, or virtually none. It'll be like a 200,000 to 1 ratio of products to reactant. And that's what we're showing over here. On the right, we have an equilibrium here. All the ATP is drained out, it's been burned, there's nothing left. Okay? And so this is at equilibrium. And this is not equilibrium over here. Yeah. Right. And the delta G, by the way, if you were to look at this as standard conditions, the delta G of this is equal to negative 30.5 kilojoules per mole, which tells us that this reaction will heavily favor the breakdown products. Now, that's not a steady state. That's taking ATP, letting it come to equilibrium. That's not what biological organisms do. That's not how we use 120 pounds of ATP. That's the conception that you first started off with. Okay, I got to find, somewhere on my body to store 120 pounds of ATP on a daily basis. No, that's not what we do, okay? And you know that to be true, obviously. So here's what we'll do on the bottom here. We'll draw a very similar thing here. But we're going to add some things to this. This is more in line with what we mean by a steady state. Okay, draw a series of tanks again. Okay, we'll use the same sort of coloring here. ATP up here, and very little ADP and inorganic phosphate. Okay? And we have this then potential for this, of course, to drain in here, and as it's draining, it's magically converting to its breakdown products. Okay, now, here's the thing about a biological organism. The biological organism will remain like this. Yours and I cell will have an enormous amount of ATP, even though it has this huge potential to drain it all into that. But it will keep this level of ATP. And this very small level relative to that level of ADP and inorganic phosphate. How does it do that? Well, it has another pipe. I should have left an opening here. But it has another pipe that will go like this. That can take that ADP, drain it out, and pump it back up here. And by the time it reaches up to here, it's now converted to ATP, and it drains back into this. And you'd have to have some pump to do this, right? So if you think about it this way, we can have, let's say, I don't know, some sort of, my drawings is not going to be very good, right? So, and then there's this big thing right here, and that's a pump. Yeah, that's awesome drawing. Way to go, Aaron. Okay, pump. Okay, and that pump is sucking that ADP and intermediate phosphate, is pumping it up the pipe and is converting it to ATP. That pump is catabolic pathways, right? So that's a steady state. That's how you burn through 120 pounds of ATP. You burn it, you regenerate it. You burn it, you regenerate it. And so that pump has to be fed with something, right? And you think of like an electric pump or a gasoline pump, but it has to be fed with food. Question?
It would be just as accurate to say that we synthesize or generate 120 pounds of ATP as well as consume.
Yes, I thought about that even during the question. So if you didn't catch what he said, it could be just as accurate to say, how much ATP do you make on a daily basis? About 120 pounds, yeah. Your cells have a small reservoir, like if you think about your skeletal muscle, there's a small reservoir of ATP there that could last within like a couple of seconds, maybe even shorter time than that if you were to take off on a sprint. And then you have to start to make it, okay, again. And that's these processes. Okay, but this is the idea of what we mean by steady state. Notice this is not at equilibrium. There's something propping us up away from an equilibrium state. This is the equilibrium state. And that's what I said. You'll be 6 feet under if your ATP levels reach this. You're no longer going to be able to function. Okay. Other questions, statements, thoughts? Isn't that a great way to start off the class? I mean, let's be honest. That's awesome. Okay, here's what I want to do. I do, because I'm glad I remember this. Let's go back here. I should have done this at the beginning. We want to hold study sessions, so I'm going to take a little break from the material. Which of the following times would work best for you to attend Matt's review study sessions? These are some times that work really well for him. Let me know. I'm going to give you a minute to respond to that, and we'll see what the responses are, and then maybe I'll poll you one more time. Okay? All right, go for it. Shouldn't take you a minute, but real quick, let me know. Okay. You can talk to each other too. I mean, there's nothing much to talk about, but you can talk to each other. And these are just, like every week on a weekly basis, by the way. Okay. You have 10 seconds left, so submit an answer, please. Okay, let's check this out. Oh, right. So we got, a wide smattering of things. Let me do this. I'm going to re-poll you, but I want you to only, I know that the options are going to be there, but I want you to only respond to Fridays from 3 to 4 or Mondays 3 to 4 or none of the above. Okay? So those two, exclude these because these are shorter percentages. Okay? All right. So I have to clear this. And I'm going to go again, lock, there we go. Okay. I'll give you about a minute-ish, 45 seconds. Okay. Is it going? Oh, did it not go? There we go. Poll locked. Awesome. Okay, now you go. Okay. Wait a minute. Actually, I'll just wait till our count here gets to be about 100, because that's what we had. Okay. Do. Okay, great. Stop. Lock and load. Okay. Oh, jeez. Okay. Okay. Well, I'll talk to Matt about it. Mondays 3 to 4 or Fridays 3 to 4. So, okay, I'll remember that. I'm not going to make an announcement. Okay. Some of you are persistent on saying Wednesday and Friday. You're like, nope, those are the days. I'm going to say it. I'm going to do it no matter what. I'm going to force you all to come to my reviews. Okay. All right, so steady state. Now, there has to be something, right, that regulates these processes. As you start to consider the steady state, for instance, I mentioned taking off on a sprint. That's going to put a greater demand on this drain, right? You're going to start to use a lot more ATP, which means that this better start to go up as well. And so there has to be some way to regulate that, and that's what we're going to talk about. And so how do pathways do that? The very first thing that we want to talk about is just a pathway, right? And the design of a pathway that will allow this to occur. Now, what you're looking at here is a metabolic, or a hypothetical metabolic pathway, okay? And so I have another poll everywhere question for you. And this is all we're doing today is poll everywhere questions, okay? But I think that's okay. All right, so let's do this. Talk to your neighbor about this question. Maybe. No, we already did that one. Don't do that question. We're not going to do it. 120 pounds is the right answer. All right, the figure below is a hypothetical metabolic pathway with forward and reverse rate shown above and below the arrows. Forward rate, reverse rate. Forward rate, reverse rate. Okay? Click the set of arrows of the reaction that you feel will be the regulatory step of this hypothetical path and discuss reasons why you feel that that is the case with your neighbor. So what do you think? This one, this one, this one, this one. Okay, what is going to be the step that should lead to regulation? You're like, how am I supposed to know that? Well, I don't know. Maybe you do, maybe you don't. Okay, remember, you're not getting right or wrong for this, okay? But talk about that with your neighbor. Think about it. I'll give you a minute and a half. Your marks, get set, go. Okay? All right. Okay, about 10 seconds left. So submit an answer. Now, okay, so there you go. Note on this type of question, if you don't have a smartphone or a computer, you can't really answer this type of question, okay, because you have to have an image to click on. If I ever ask a question like this, all right, I will also ask something that day that allows even people with flip phones to respond to. Okay, so you can text it. So let's go ahead and look at what people said here, and there we go. All right. So, you know, they're kind of all over the place. Okay, this has a higher concentration than I think most of them. This has probably the weakest concentration of responses. All right, so let's go ahead and address this. Right, all metabolic pathways look something similar to this. Now, let me define what I mean by that, and let's look at define some things before I give you the answer of what I feel is the most important step of regulation here. Looking at this, I think that this step here and this step here are very similar to one another. And what I mean by that is that their forward rates are higher than their reverse rates. Right? Now, these steps here and this step here are very similar to each other, meaning this, that their forward and reverse rates are very, very similar. Okay? All metabolic pathways are comprised of at least two different types of reactions, what are illustrated right here. The ones in red, these guys, would be called near equilibrium reactions. Now, what do we mean by near equilibrium? Okay, near equilibrium means that they're essentially reversible. Their delta G's are about 0. Okay? They are essentially at equilibrium or near it. Their forward rate and the reverse rate are almost the same. Okay? And so if we were to look at just the conversion of B to C or just the conversion of C to D, that delta G would be about 0. Now, the other thing to note about these is that they're very, very rapid and they're reversible. Now, very rapid, let's look at this. Look at these two rates versus these two. There's an order of magnitude difference between them, at least. An order of magnitude difference. Meaning that the conversion of B to C and the conversion of C to D is much more rapid than the conversion of A to B or from D to E. They're fast. Okay? Now, from a metabolic standpoint, what that means is that there are, because these are rapid, there's lots of enzyme. Or that enzyme is very efficient, or both. Okay? But if you have a lot of enzyme, you're going to bring a reaction to equilibrium fairly rapidly. And so in those cases, whatever those enzymes are, you know, have names for them, this is a hypothetical scenario, whatever they are, they're going to be in a lot, or they're going to be high in abundance in the cell, and they're going to bring that particular reaction close to, if not at equilibrium. And those are near equilibrium reactions. Now, last thing here, they operate via mass action principles. Le Chatelier's principle, right? If this goes up, then it shifts in this direction because they're at equilibrium. And then that will cause this to go up, and that will shift in this direction. Or vice versa, right? If this goes up, then it will shift in this direction. Okay? They can go in either way. They're reversible. And they're just going in the direction that they're essentially told to go in based off of the availability of the substrate present. Okay? Those are near equilibrium reactions. Now, those other ones, the bookends, those would be far from equilibrium reactions. So let's go to our next slide. And far from equilibrium reactions are ones whose delta G is negative. They're not at equilibrium. Notice that the forward rates in each case are larger than reverse rates by a significant measure. In the case of the first one, it's 100-fold different, right, or 100 times higher. It's twice as high in the end. So they're not at equilibrium. Equilibrium, remember, technically means that the forward and reverse rates are equal to each other. It's not the case with these. Now, you will also notice, and this is a relative term, and I said this already, these are actually fairly slow relative to their neighboring near equilibrium reactions. So these are slow, or they're rate-limiting reactions. Okay. Now, VF, just by the way, is velocity of the forward step. That's what VF means, velocity of the forward step. Okay. And here's the answer to our question. These usually regulate flux. Now, I haven't defined flux, but these are regulatory steps. Okay. These enzymes, okay, are regulatory enzymes. Okay. Regulated enzymes. They are typically in lower concentration. The enzyme is in typically lower concentration, but they can also experience fairly drastic decreases or increases in their catalytic rate based off of something that's going on in the cell that's causing that enzyme to function better or worse than it would without that thing going on. We'll talk about the how to that as we go on. Okay, but that's essentially the idea, regulatory enzyme. All right, so if you were a person that put a little star there at the bookends, one of the bookends, and you're headed in the right direction, these steps, okay, let me say this, these are rate limiting steps. RLS, rate limiting steps. And if you've gone over like enzymatic mechanisms, which we're not going to really do that much in this class, But if you've gone over those, you'll talk about a rate-limiting step of an enzyme that slows the whole thing down. Well, that's the same thing with metabolic pathways. There's a rate-limiting step of a metabolic pathway, or a couple rate-limiting steps, as we're seeing here. And those then steps, if we change the rate of those, that will change the overall output of the pathway. Now, let me give you an example here. Okay? If I were to take that rate, that forward rate, and take it from 10 to 20, then my ability to produce B would double. Now, what's going to happen once I start to double B? The next two steps in the pathway are going to occur just like that, right? Real fast. So I have not only increased the ability to produce B by double, but I've increased the ability to produce D by double. Okay? Because the next two steps are going to be so fast. Now, it slows down a little bit at the next step. Okay, and there's a lot of, and this is where metabolic regulation gets a little complicated. It's not just a single step in a pathway that's responsible for regulating it. At one point in time, biochemists believed that to be true. Research has demonstrated that that's not true. It was easier to be a biochemist in some senses 50 years ago. Okay. In other senses, it was much more difficult because the research moved at a snail-like pace. Okay. Now, the term flux, real quickly, J. Okay. If you see J, we mean flux, and simply that's just a fancy term for the velocity or the rate through a pathway. I think that the term was probably coined to avoid confusion between, velocity or rate of an enzyme, so they talked about flux. It does make me think of Back to the Future, though, I'll be honest with you. The flux capacitor. I have to watch myself, right? Because I was an 80s kid,
You have every right.
Okay, yeah. See, I know that there's still people in this generation that have seen it, although most of you were born past the fact that that movie was being made, which is really a comment on my age. Yeah, 1.21 gigawatts, exactly. But it's classic. Flux capacitor. Anyway, okay. I'm sorry. I got all confused. So, okay, real quickly, just to be clear, this is not the flux capacitor, and time travel has yet to be demonstrated as being possible. Okay, you're trying to travel every day. Okay, we'll have that conversation later. All right, now let's do this. Any questions? Okay, now remember, Wednesday I said 75% of you don't ask a question, not because you don't have a great, brilliant question, but because you are afraid of talking in front of people. Or not maybe afraid, but you just are not overly fond of it. Okay? And I said there's a solution to this. If you go on to right now, slido.com, and you type in this, you can ask a question and no one will know about it. And I'll keep returning to this and I'll try and answer your questions. Be nice in this format. Okay, it's not a time to bash someone. All right? Yours truly. Don't do that. I mean, you can if you really want to. I'll never know who it is. And I'll just okay, shrug it off. Anyway, okay, but you can ask a question. If it's way off topic, I'll just ignore it or make fun of someone. But no one will know I'm making fun of you except for you. Okay, but ask a question. Okay, and certainly I won't ask questions on. Has anyone said you look like Ben Stiller? See, that's what I'm talking about. Just ignore that. All right. The answer to that question is no. I've never been told that. Okay. All right, now, let's go back here. We've got these two bookend reactions. See, this class can be a lot of fun because the material, first of all, is really fun, but then I give you these opportunities to make those little comments, and that can be a good way to break up some material. Okay, but let's look at these bookends, and notice here, and this is what I was saying, research has demonstrated that there are usually in a pathway more than two rate-limiting steps, or more than one rate-limiting step. Okay, so we then have to figure out, well, which of those has a greater contribution to the overall flux of the pathway, and how do we know that? And so your book brings up this topic, something called the flux control coefficient. Now, what time is it? We got 10 minutes, so we can start this topic, no problem. Flux control coefficient, I'll define, well, it's a little bit harder to define, but let me say this, okay? We're going to refer to this as C, okay, the C value. And it is a way to determine how great of a contribution an enzyme has to controlling the flux of a particular pathway. Let me say that again. The flux control coefficient is a means to determine how great of a contribution a particular enzyme has to regulating flux. Okay. And we're going to look at it. Your book, the suggested text in box 15.1. So we're in chapter 15 here. I don't know page numbers there. But it has a discussion on flux control coefficient. And the surrounding text around that box will have that as well. Okay. Your book goes into more detail than I'm going to in class. It talks about elasticity constants, and it talks about a response coefficient. We're not going to do that. So you can just ignore those types of terms. Flux control coefficient is really all we need. Now, here's what we can do, and here's how we've come up with this idea of flux control coefficient. Okay, we can measure, or hopefully we'd have some way to measure the flux through a particular pathway. And again, by flux we mean just A, ignore all the middle steps, goes to E. Okay, how fast is E being produced? That's flux. And then because we know it's a pathway, what we can do, and there's great experimental ways to do this, we can change the concentration of particular enzymes within that path. Okay? So just pick one. Doesn't really matter which one. Well, I mean, obviously it would matter in a research sense. But for our illustration here, it doesn't really matter. Just pick one of those and start at none of that enzyme. For instance, we could take the enzyme that catalyzes this step, okay, and just remove it altogether. If you remove it altogether, right, biological reactions don't occur without enzymes. The metabolites that we have in our cell are kinetically very, very stable, ATP included. ATP, if you set ATP out on the shelf, all right, with a ton of water even in it, right, but no enzyme, it would remain ATP. It has this great potential to become its breakdown products, but at a rate, it's not going to do that at an appreciable rate. Another great example that you probably have a little bit more familiarity with is this. Sucrose, table sugar. Does it break down very fast when it's sitting on your table? No. But if you eat it, right, you consume it, it'll be gone within the next hour. And if it's my kids, okay, you'll see the effects. Let's just put it that way. Okay, so those are kinetically stable molecules. So you have to have an enzyme. So you remove that enzyme that converts B to C, and you would have all the way down here no flux. Okay, even if you had all the other enzymes present, you'd have no flux because you couldn't get B to C. You could get A to B, but you can't get B to C. Okay? Now, start to increase that enzyme concentration. And what we're doing when we talk about the flux control coefficient, and they're illustrated in it here, is essentially we're just taking the instantaneous rate of flux versus the the change in enzyme concentration, which is just the tangent to that line. It's a derivative. Okay, and you can see that here. Okay, you take the tangent to that line, that is C. Okay, the slope of that tangent, okay, is going to be C. You'll notice down here, let's put it down here, if we take the slopes, let's take this point right here, take the slope of that, it's, you know, like straight up and down. The slope is almost 1. You come all the way out here, and look at how that slope's just kind of fallen off. Notice that what's happening as you get more and more and more and more and more and more of that enzyme becomes less and less and less and less important in regulating flux. Why? Because it's getting closer and closer to equilibrium. Okay? And so when we look at a flux control coefficients, okay, these will vary from 0 to 1, where 0 means that that enzyme has 0 influence on the flux of the pathway, and 1 that enzyme is entirely responsible for changing the flux. So if there's only one step in the pathway that's regulating it, it will have a flux control coefficient equal to 1. Okay? If there are multiple paths, then it will be a value lower than 1. I'm sorry, multiple reactions, there will be a value lower than 1. Okay. Now, they will always add up to B1. So let me give you an illustration here. Okay, this is just essentially the same slide, but now I've put hypothetical flux control coefficients above each of the enzymes represented in our hypothetical metabolic pathway. A C value of 0.8 means that that one's really important in regulating flux. 0, 0, no importance whatsoever. Those are our near equilibrium reactions. And then 0.2 has less bearing on the overall flux of the pathway, but it's still important. Okay? And you add all those up, and they will equal a total value of 1. Now, again, your book goes into more detail describing how do we calculate flux control coefficients. You can look at that on your own time if you want to. I'll hold you responsible for what I said in class. In fact, that generally is going to be true all the time. Okay? If you hear it in class, you're going to be held responsible for it. If not, then I'm not going to hold you to it. Okay? Unless it's one of those review tutorials that I said listen to. Okay. So that's pathways in terms of generally how they're designed and how they can lead to regulation. Questions? Yes?
So J is our flux on the graph.
Correct.
So that we test the concentration of the enzyme where we're going to take the derivative and get our tangential line. We determine that based on the maximum flux rate.
Right. At that particular point.
And that will happen even if all those other enzymes aren't present?
No, those other enzymes have to be present. You'd have to have the other enzymes. So you would hold, so the question really is, first of all, you're measuring J flux of the entire pathway, right? And then we're finding our flux control coefficient based off of where we are in a particular curve at that enzyme concentration. Okay?
So it's really relative enzyme concentration.
Yep. Well, yes. Yeah, we're not, yes. Because these things will move. In a biologic organism, your enzyme concentration will go up and down. So it would be relative to the other ones, yes. Experimentally, you would isolate the pathway.
Yeah.
You would hold all the other enzymes constant, and you would change one.
Right.
Okay. We can do it in a biological organism now that we have genetic engineering possible. It's a more difficult measurement, for sure, because there's lots of variables that lead into it. But you can do that. Yeah. Okay. Other questions? What about here? I mean, aside from me and Ben Stiller, are far from equilibrium exergonic spontaneous? Yes. Delta G's are negative. By then definition, they would be spontaneous and negative delta G. And again, no. Okay. All right. Now, one more thing here, because we've brought up biological organisms and the complexities of these things. Understand that this is a nice hypothetical pathway. A goes to E. Everything's nice. We only have, 4 enzymes. That's nice. However, what about this? What about pathways that branch from other pathways? Remember, I said that there's thousands of pathways, and they are not running in isolation from one another. They are sharing metabolites. They're working in coordination with one another. What does that mean? Well, if you have branching pathways, the enzyme that would catalyze this, D to X, would actually get a C value that's negative. Okay. All right. Now, all of a sudden, my values don't equal 1, so I'd have to maybe increase this to 0.5 or something like that. But things that take away from that path are going to get negative flux. Okay. So we're not going to, spend a ton of time hurting our brains on not, calculating these things. But gives you an idea. Question,
So
yes?
then if there's products from other reactions that feed into to this pathway, those would have a positive flux value because they're adding more.
Correct. Yep. So the opposite would be true. If you add something to this, you can get a positive value. And then, but again, all the C's are going to equal 1. Yeah. So, okay. All right. That is a great place to stop. We will come back on Monday and we'll start talking about how do we regulate those enzymes.